said go. So we got to go. Let's go. All right. So, hi. How are we? Okay. So we are going to be working on note sheet 33-34. Okay. So that is a crazy combination of the one that you picked up today and yeah, well, usually we have extras, and then the one that you did over what the video's on. So that's the crazy combination of note sheets that we're going off of today. I just don't know where all the extra ones went. So if you don't have one, STV1. Okay. Okay. And then we're gonna start some work in the textbook. That's why we put the textbooks out. The textbooks are also on Canvas, so you can go from there. Tomorrow is Wednesday. Tomorrow you're gonna have a formative, okay, on 3.1 to 3.3, maybe even some 3.4. You will also need your Chromebook and some earbuds for tomorrow because you are going to be watching the video tomorrow after you get done with the formative and taking notes on it. Okay? Little log joke for you today. Peak log is base 10. Natural log is base E. Ha-ha. E. Ha-ha. All right. So, where are we at? Okay, perfect. We're on the one from today right now at the top. Solving simple logarithmic equations. Okay? So, logs, I'm not going to lie to you, in terms of logs, if you don't have this written down somewhere, you are going to want to have this written down. So, if we've got a base, and we take that to a power, and that equals some number. I'm going to call it, it's actually called the argument. So I'm going to call it the arg. Okay? Alright? So that is exponential form of an equation. Because we have a base with an exponent equals something. That's an exponential equation. That is the same as this is the logarithmic form of that equation. So for instance, over here on the side board, we have 3 squared equals 9 written out as our exponential equation. That is the same as log base 3 of 9 equals 2. Logarithmic equations find exponents. They are exponent finders. Okay? So what this first one here is saying is it's saying 10 to the negative 2 power is equal to x. Well, 10 to the negative 2 power is 1 over 100. So we have that. We solve logarithmic equations by switching them into exponential form. We solve exponential equations by switching them into logarithmic form. It's a dance of wonderment and beauty. With that being said, what's the answer to number 2? What is x in number 2? 16? Okay. Because it becomes 2 to the 4th equals x. is 16. Okay. You solve me those. What's the base here in number 3? E, right? Okay. So this is E cubed equals X, which would be the exact form of it. 20.0855 would be the approximate value of X. Out of curiosity, which one do you think we prefer? On top, the exact one, E cubed. Okay. Right. What's the base over here? 10. An exponent of 1/2 means what? Yeah. Smaller to what? What does an exponent of 1/2 mean? Anybody? No? Square root. Square root. The approximate. Again, which one do you think we prefer? Top one. Exact. Takes the rounding out of it. Okay. Now, I'm not saying I saw this on anybody's paper, but an exponent of 1/2 doesn't mean multiplied by 1/2. Right? That is a very common mistake that people forget. Okay? It means take it to the 1/2 power, which is square root. Okay? All right. Let's graph logs. So, exponential functions, we'll take a step back to, when did we talk about exponential functions? Way back in September. Okay? Exponential functions, remember, either grew or they decayed, right? But they all had a horizontal asymptote. And that moved depending on shifts, right? But its base was at y equals 0, right? Okay? And then we always went through the point 0, 1, or 0, a, depending upon our function and what we're dealing with. Okay? Depending upon our shifts and all that fun stuff. Okay? Now, logarithmic functions are inverses of exponential functions. So when you're finding an inverse, we switch the x and the y. The domain becomes the range, and the range becomes the domain. So instead of having a horizontal asymptote, we're going to have a what kind of an asymptote? We're going to have a vertical asymptote. Okay? So that means that it's going to start out, oops, I missed. We're going to have a vertical asymptote at x equals 0. Okay? So if we go back to y equals b to the x, our domain was all real numbers. Our range was y was greater than 0. Our horizontal asymptote was at y equals 0, and our y-intercept was at 0, 1. All that fun stuff. Okay? So now we flip that around. So the domain of y equals log base b to the x is now going to be the old range. So the domain here now is going to be x is greater than 0. Our vertical asymptote, which we just got done talking about, would be at x equals 0. Our range in the inverse was the domain in the old one, so that's going to be all real numbers. And our x-intercept is going to be 1, 0. So our function is going to start out along the vertical asymptote. Then it's going to make a rapid turn and head on out to C. Okay. Now, that's the general one. Let's put it into special bases. So we've got a special base of 10 and a special base of e, correct? Okay. So we are still going to have x equals 0 as our vertical asymptote. Reason is we have no shift in our x right there. Okay? So there's nothing being added or subtracted to that. So our vertical asymptote is going to stay at x equals 0. Okay? We will still go through the point 1, 0. Reason being, if we plug that point in, whoops, that was kind of funky. That was, the black one was my stringing right there on my bracelet. 0 equals log base 10 of 1. Remember how I said logs were exponent finders? Said that earlier? Okay. What exponent do I have to put on 10 to get 1? 0. Anything to the 0 power is 1. The next point that it would go through would be the point 10, 1, because it would be log base 10 of 10. What exponent do I have to put on 10 to get 10? Answer is 1. What would the next nice one be? The next nice point that it would go through? Nope. What would the next? 100, 2 would be the next one, because the exponent of 2 gets me 10 squared is 100. Okay? So there is all of the nice, neat points that it goes through. So it really takes a serious turn here. The next one would be 1,000, 3. And so on and so forth. Okay? Natural log, still going to have a vertical asymptote, x equals 0. Still going to go through the point 1, comma 0. What would the next point that it goes through? Or the next nice point? Right? Next one would be e squared. Next one would be e cubed. Good time. Properties. Properties. Okay. So now we're shifting gears into the properties of logarithmic functions. This is what you watched a video on over the weekend, I believe, right? Okay. All right. I'm just admiring all the graphs going on up here. Color coded and everything. I love it. Okay. All right. Okay. So in all of these properties, B, U, and V are real numbers. B can't be 1, C can be any real number, all that fun stuff. Okay? So we've got 3 logarithmic properties that we're going to use to expand and condense and solve and all that fun stuff of logs. So the first property is called the product rule. The product rule says that in the argument, remember this part of the logarithmic function is called the argument. In the argument, if you are multiplying 2 terms or 2 different things, we can split that up into log base b of u plus log base b of v. Multiplication goes with addition. The quotient rule says that in the argument, if you're dividing something, then you would be subtracting. And finally, the power rule says that if your argument has an exponent on it, we can take that exponent and bring it out in front because it would just basically, so like if we had C or U cubed there, if we had like U cubed there, we could use the product rule, and the product rule would say, well, that would be log base B of U plus log base B of U plus log base B of U. Well, now when you're adding, there's 3 of those, so that's where that comes from. Okay? Good time. Change of base formula is the other formula that we need. It's for you guys, it's way down at the bottom of that page. Okay? And so what this is saying is because on your calculators, on these scientific calculators or the graphing calculators or all that stuff, they're limited. Okay? So they're limited in what they can do. And on these scientific ones, they can only do log base 10 and log base. Okay? But that's not the only kinds of logs that we're going to be evaluating. So in order to do that, what we have to do is something called the change of base formula. And the change of base formula says that if you need to evaluate this log, you're going to take the log base 10, or the standard log, and divide it by the log of base b. If you're not a log base 10 type of person, you could also take the natural log of u and divide it by the natural log of b. I will tell you this. This is just for you, Courtney. I'm not going to tell anybody else, okay? Right? On these TI-30 calculators, that seems to be the most common calculators out there, when I type in log on my calculator, and when I hit the log key, notice how it opens up a set of parentheses. I have got to close that set of parentheses around the u before I hit the divide and then close it at the end. Otherwise, your answer is going to be all kinds of funky. All right. Okay. Good times. All right. So in maths, there's this thing called expanding logs, and then there's contracting logs, which is what we're doing here with the expansion of logs, and going the other direction. All right. So what we're going to do is we're going to take this argument and we're going to break it up. So really, that argument is 100 times x times y to the fifth, right? Well, multiplication, which property is that? Product, quotient, power, or change of base? That's product, right? So we could write this as log of 100 plus log of x plus log of y to the fifth power. And I've expanded it, right? What's wrong? Like, so you're saying I should apply the power property? Well, just have the breaks. Maybe we're not all there yet. Okay? That's the third one that I want to look at. Is there anything that I can do with the first law? Who?
You can simplify it.
To what?
To 2.
To 2. Yep.
And to the power of 2.
Is 100, right? Yep. So this one is actually 2. Okay? Is there anything I can do with the middle one? Nope. So I'm going to leave that as plus log base x. Now, my dear, is there anything I can do with the last one? And what property is that? Power. Yeah, power property. Yeah. Yep. Power property says we can take this exponent of 5 and put that out in front. And get that. Okay? What I would like you, yes, you, to do now is I would like you to expand 2. Oops, 2's on there again. There's 2 on there again. 2, 3, and 4. That was weird. Two natural logs of x minus 3 natural logs of y. Would you agree with that for number 2? Okay. Oof. Oof. Do you agree with that so far? Yeah? Do we agree with this? Yeah? But what's wrong with that third one?
It's technically 10 times the.
So we got to break that one up too. So we're going to break this one up into Mr. Alley, did you have a question? Okay. Right? Yes, ma'am.
For the log times the cube root of x.
Log of the cube root of x?
Yeah.
Mhm.
Could you do get x to the power of one-third?
You would. I would love it if you would make it to the x to the power of 1/3, because then it becomes 1/3 log of x, right? Plus 2 logs of y. Right? Minus log of z. Minus 1. Now, if you put the minus 1 in for it, then minus log of z, that order doesn't matter, but they both get subtracted. So I would get here 1/2 times the natural log of the quantity x plus 4. I can't break up that x plus 4 because I don't have a additive property if I'm adding things in logs. Good time. Okay? Now, we can work backwards. So now we'll give you the expanded version, and we're going to ask you to find the condensed version. Okay? So you work backwards. So we first, and when we're expanding, we apply power or quotient, then, quotient or product, and then power. When you're condensing, you're literally working backwards. So you're going to apply power first, then product or quotient. So this would become log of x to the 1/2 power minus log of y cubed, which would be log of the square root of x minus log of y cubed. Since it's subtraction, that's going to become log of the square root of x divided by y cubed. Agree? Okay?
Do you put parentheses around it, or is it fine?
It's fine like that. It's also fine like that. Okay? You do 6, 7, and 8. Now, actually, on your sheet, it's 2, 3, and 4. But mine, it's 6, 7, and 8. I don't know why I did them either. Okay? So you get that? So in the end here, and I'll show you a couple of different ways to get it, but in the end, it's going to be the natural log of 2 divided by xy cubed. Okay? Here's how I think about it, and mathematically I'll show you how that goes, and then you'll see both ways. When I think about it, I think about anything that comes after an addition sign gets multiplied, and anything that comes after a subtraction sign gets divided. So after an addition sign, it goes on top. After a subtraction sign, it goes on the bottom. Okay? Mathematically speaking, how that is I am going to factor out a -1 here, then that's going to become positive natural log of x plus positive natural log of y cubed, which is going to be minus natural log of xy cubed. So first argument goes on top, second argument goes on the bottom. For that. Okay. This would be natural log of x to the 5th plus natural log of y squared minus natural log of z to the 1/2 power, which is the square root of z. So this one would become the natural log of x to the 5th y squared, all divided by the square root. Log of the cube root of 5x minus log of y to the 4th plus log of 9, because it would be 3 squared, which is 9. So on this one, I got log of 9 cube roots of 5x all over y to the 4th power. Questions? So if there were parentheses here, then it becomes like the one from 2 problems ago. Okay? But there's not, so the only thing that goes on in the basement is this middle term right here, because it's the only thing being subtracted. With me? This part right here is being subtracted. So this part goes downstairs. That part's being added so it stays upstairs. Okay. Last thing is change of base formula. Okay. So if we wanted to find the exponent that goes on 3 to get 8, we can get close, but to be like rounded or to be exact, we've got to kind of know what it is. Okay? What do we think it's close to? Close to 2? Bigger than 2 and close, or less than 2 and close? Less than 2 and close. Why choose 2? So 3 squared is 9, so it has to be less than 2, because log base 3 of 9 would be 2. Okay? All right? So I would agree with that. So on your calculator, in court, this is where your calculator will come into play. Okay? Where that closing of the parentheses. Okay? Because when I go to type this in, so it's going to be log of 8 divided by log of 3, or natural log of 8 divided by natural log of 3. Now, when I go to type that into this TI-30X2S calculator, I get log and then open parentheses. Okay? That's what happens immediately when I type it in. So what I got to do is then I have to make that 8, and then I've got to close that parentheses before I do the divide. Then when I hit log again, then I got to close that parentheses again. Same thing with natural log, I believe, on this calculator. Clear natural log. Yep, same thing. So it doesn't matter which way we do it. Okay? So when you do it that way, you would get 8, 3. I get approximately 1.892789261. Now, I will tell you that I see some more fancier type TI calculators out there, and those, wink, wink, nudge, nudge, do you know how to do it? So first yes or no. Okay, and then I think with this one, nope, yours is not the fancy. Okay, so you guys do it the long way. That one, fancy. Turn it on. Calculator. Okay, and then when you hit the log, you should be able to fill in the base and the argument. And so then it does it for you. Yeah. Okay? Fancy pants. Now, do you have both of these? Log base 4 of 16? Just that one? We don't even need that one. What is it? 2. Yeah, that one's 2. I mean, but it'll still work with change of base. So if you do log of 16, and then make sure you close your parentheses, and then divide it by log of 4, you should still get 2. I still get 2. But if I don't close off that parentheses, then I get 1.4244802165. Okay? Because what it's doing is it's calculating the log of 4 and then dividing that and then calculating the log of that whole thing. Okay? Last one, log base 6 of hundo. What do we get? Zero 1.94418. Love it. That's what I got right here too. Awesome. Good time. Okay. Now, what I would like you to do for the remainder, like the next half hour or so, is you just need some practice. Okay. And so we have textbooks scattered about the room. And we can always get more if you want your own personal type one and you're too lazy to walk to the back of the room to get one. In the open cabinet next to the door is a whole cabinet full of textbooks if you want that. If you want to share with your neighbor, share with your neighbor. Okay? But on page 308, there's a quick review, numbers 1 through 10 that you can do. And then in the 3 exercises, you can do 1 through 23 odd. Number 33 and number 35, and then you can skip to page 317, open door, and then you can do numbers 1 through 21 on there. Okay, all right. And we want you to be working on these and practicing these in your own, on your own paper for this. This would be good practice for you.